Hello guys, in this video I'm gonna introduce you to the new concept of power, the electric power. So there is like many forms of power or energy. We have like the magnetic energy, we have the kinetic energy, we have electrical energy. That's basically our course in here. Okay, so we don't deal with the energy directly, but we deal basically with power. Power is the rate of energy, you know. It is basically joule per second. Joule is the unit of the energy, the work done, you know. So, or the total basically power in some certain amount of time, during some certain amount of period of time. Okay. But we always like deal with power. Power is the rate of energy, joule per second. How many joules I consumed per second. Okay. And we have again uh, energy generated or power generated and energy consumed or power consumed. Okay. So in here, for example, and of course, the power generated comes from our sources. You know, so far we studied two kind of sources. We have the current source and the voltage source. Okay. So simply the power of a voltage source or a current source is basically multiply the source current by the source voltage. But the directions is very important, extremely important. Okay. So as you see, guys, here, the direction of the current and the direction of the voltage in both the current source and the voltage source is basically the same. Okay, basically the same. So if you have the freedom to choose the currents, just assume the currents, you know, in the same direction of the voltage source or the same direction of the current source. Okay, if you have the freedom to do so. If the problem doesn't assume like a certain direction for the current or the voltage. Anyways, so just if you know the current and the voltage, be sure of the directions, okay, and then multiply them by each other. This will give you the power. And the unit of power is watt or joule per second, whatever you like. Or you can say ampere per volt, because basically, as you see here, this is voltage, this is amperes. So you can say VA, V dot A, or V multiplied by A or times A, or basically what? It's always better to use watts. W, just write W. Okay, or joule per second. J and S divided by S. Okay. Okay, this is for the power generated. Now, where is the power consumed? It is basically consumed, or basically we can say, physically it's converted. So the power consumed in the resistance, okay, the resistance that you see in the electric circuits, it's actually not consumed. The power doesn't vanish. It is converted to another form. And in the resistance, in your electric circuit, it is transferred to heat. So whenever you see a current flowing through a resistance, after some time, it's going to develop heat. This heat is basically the transformation of the electric energy into thermal energy. Okay? So that's base, and this is like all the time. Any electric device you have, like for example, a fan, like a ceiling fan, for example, the ceiling fan has a loss. What is this loss? So the ceiling fan, should convert the electric energy, your voltage that comes out of the outlet, into like, kinetic energy. But some minor fraction of it goes or consumed, as a loss, as thermal energy. So you can't like neglect that. Okay, and that's because any electric device has a certain like resistance, equivalent resistance. So now for the resistance, what is the laws that calculates the power consumed in the resistance? Okay, so if you have a resistance R like this, okay, you have the voltage in this way from negative to positive. You have the current going in the opposite direction. I always assume the current in the opposite direction of the resistance if the opposite direction of the voltage of the resistance in the resistance. Okay, so with that Power is equal to IR multiplied by VR. Same law. VI, VI, VI. Everywhere. In the current source, it's VI. In the voltage source, it's VI. In the resistance, it's also VI. V multiplied by I. VR multiplied by IR. Okay? But we know from Ohm's law that V is equal to IR, or the voltage of the resistance equal to the current of the resistance multiplied by the value of the resistance. So I'm gonna remove V here and put IR. So we have I multiplied by R by I multiplied by I multiplied by R. So it's I square R. So that's the first law. This is the second law. And basically you can also remove the R. I'm sorry, remove the IR and put I divided by R. So that will give you VR multiplied by VR divided by R. So that's V square divided by R. The voltage of the resistance square multiplied divided by R. So you have three laws here. You can use any of them. Any of them. Okay? Finally. Not finally, just finally for this introduction, then we're gonna go to examples. The law of conservation of energy. This is very important, extremely important. Okay? Why I'm gonna tell you in a moment. So the conservation of energy, means that the power you generate is the power you consume. So the power that comes out of your sources, the voltage source and the current source, equal to the power consumed in all your electrical elements, the passive elements. Okay, and that's very important. You know why very important? Not because of course it's like very very useful law for any like kind of scientific field, but even for you as a student when you like solve an electric circuit question, and you want to verify if your answers is right or wrong, just apply this law. Just calculate, if you calculated all the current and the voltage in the circuit, calculate the input power and calculate the power consumed in the resistances, for example. They should both equal. If you find a big difference, of course there will be some fractional differences because of the errors, the rounding errors, that's fine. Okay. But if you like see like drastic change or drastic difference between them, you have a mistake. So I'm gonna now solve examples, just three simple examples, but you can take the idea and apply it to any kind of electric circuit. So this is the first example here. I'm gonna solve this example just like what we did in our examples so far. Find the currents and the voltages in all the elements of the circuit. So we have here, find, let's assume this is I. We have here I1, find I1. We have I2, I2, find I2. We have here V1. We have here V2. And we have here V. And as you see, guys, I assumed the current and the voltages in the resistances opposite to each other. Okay, this is very important. And we have here the voltage of the battery. It is the same as the current of the battery, which is Mr. I. So we don't need to do anything here. Okay. So I'm gonna solve this like simple circuit. Then at the end, we're gonna verify the law of conservation of energy and actually verify our solution as well. And you can apply that for any like kind of circuit afterwards. So let's do that. So we have here two resistances in parallel, this one and this one, because why? They have the same terminals. So that guy here is equal to that guy here. So the 10 ohm is parallel to the other 10 ohm. Okay. Based on that, R equivalent is equal to any one of them, like 10 ohm, divided by 2. So it's equal because they are equal. If they are equal, if you remember, guys, from our previous like video, if you have like n resistances in parallel, all of them are equal. So just take one of them and divide by n. Okay. So this is equal to 5 ohms. So let's call this A, this terminal A, and this terminal B. So I'm gonna rewrite or redraw this circuit exactly the same. Okay. This is A. This is B. This is the 5 ohms. And then between A and B, I will not put 10 and 10 anymore. I'm gonna put R equivalent equal to 5 ohms. And this is 10 volt. So now I can determine I. I simply, or just to make it like more clear for you, the 5 ohm and the R equivalent are in series to each other. Why? Because they are common in one terminal. Okay, they are not common for the other terminal. Otherwise, they were gonna be parallel because B is different from this node here. They are not the same. They are just common in A. And they have the same current because I, the current I, has nowhere to go. It has to pass through R equivalent. There is no branch in A to go anywhere. So we can even draw this circuit like that. And that will be 10 ohms. 5 plus 5. And that's the 10 volt. So I is equal to 10 volt divided by 10 ohms. How could you know that the voltage of the resistance here is equal to 10 volt? Kirchhoff voltage law, or even the parallel like laws, or the parallel like connections. So two things we can do. Just this is on a side. I know this is very easy, but this is on a side. So guys, we have here V, for example. Let's call it whatever, V. So this V has negative here, has positive here. This is the current I, and this is the battery. So from Kirchhoff voltage law, we can apply a loop like that. So KVL, this is the positive direction. So we can see here that V has a positive, is the same direction of the loop. The 10 volt is opposite direction, so minus 10 equal to 0. So V is equal to 10. So VR is equal to 10, R is equal to 10 ohms. So I will be equal to 1 amperes. Another solution, just on the side as well. I know this is very easy, but just to refresh our information. Another solution, you can say that the 10 ohm is in parallel with the battery. How come? Okay, the 10 ohm here has two terminals, this terminal and this terminal. Okay, this terminal is very simple to verify. It's basically the positive terminal of the battery. So they are common now in one terminal. How about the second terminal? Let's check. This is the second terminal here. If you go, this is actually a short circuit to the negative terminal of the battery. So they have the same terminals. Okay, so they have the same voltage. So V is equal to 10 volt. Okay, so two solutions. So we get I. Oh my goodness, this is so hard. Anyways, so we get I now. So let's go back to our original like circuit in here. So we know I is now is 1 amperes. Okay, so I will come here and make a branch. Part of it will go in 10 ohms, the first 10 ohm, and the other part I2 will go to the second 10 ohm. By common sense here, they are parallel, they are equal. So each resistance will get the same same portion, which is I over 2. So the current will be divided equal. So we can say without any complications, I1 equal to I2 be equal to I over 2 because they are parallel resistances with same, ohm, with same resistance. So it's equal to half amperes. If you want to do like it was like a nerd, so I1, for example, equal to, with the current divider rule, current divider rule. Go back to our video about the current divider rule. So I1 equal to I multiplied by the second resistance, which is 10 ohm. Actually, they are equal, so it doesn't matter. Divided by the summation of all the resistances. So 1 multiplied by 10 over 20. This is half ampere. I2, you can do the same, or you can say by KCL, you have 1 going like that. You have I1, we don't know it. I'm sorry, we know it now. So I1 here, okay, I1 equal to half. And then we have another branch with I2. So what is going in equal to what is going out. What is going in is 1. What is going out is half. and I2. So I2 is equal to 1 minus half. Oh, 1 minus half is actually half. Okay, so this is basically, to refresh your mind, about, the law, the fundamentals that we studied so far. Okay, so we know now all the currents and all the voltages. Actually, okay, we can, yeah, we just know the currents. We didn't know the voltages yet. So let's determine the voltages. So V1 is easy, I1 multiplied by 10 ohm. So I1 is basically, we said half multiplied by 10. This is 5 volt. Good. V2 is equal to I2 multiplied by 10. So again, half multiplied by 10 is equal to 5 volt. Now let's verify our solution. Let's apply the conservation of energy law, or the law of energy conservation. So the power generated is equal to, let's look at at the source. So it's 10 multiplied by I. I is 1 amperes. So 10 multiplied by 1 is 10. So the power generated equal to 10 watts. Watt on a site. Power consumed. Oh, we have 3 now. Okay, I'm gonna call this B. I'm sorry, let's make it with another color. B1, B2, B3. The power consumed in 5 ohm, power consumed in 10 ohms here, and power consumed in 10 ohms here. Okay, so B1 plus B2 plus B3. So equal to B1 I square R. So you have many, like, look guys, so basically here, IRVR, or I square R, or V square over R. We don't know the voltage, you can determine it easily, it's very easy, but I will not, I will keep it as an assignment for you. Just I square R, because we know I is 1 ampere, just multiply, square it and multiply by 5. So 1 square multiplied by 5 plus, you can here say for R2, for 10 ohms and the 10 ohms, these two parallel resistance, you know the voltage, you know the current, you know the resistance, so you can apply whatever you like. I'm gonna apply I square R as well. So I square, this is half square multiplied by the resistance 10, half square multiplied by 10, so that's equal to 5 plus this, half square is quarter. Quarter of a 10 is basically 2.5. So 2.5. So that's equal to 10 watts. And look, guys, go look. 10 watts. So the power generated was 10 watts, and the power consumed equal to 10 watts. Okay. So we verified. So now you are very comfortable that your solution is good. Okay, now let's take another example. It's a little bit more complicated, but it's exactly the same. And I'm gonna teach you also another, like, concept in here regarding the power generation. Let's check that. Here, it's a little bit complicated, not complicated because it might confuse you in the first time, because here you have like two opposite batteries. A battery with positive negative like that, and a battery with negative positive like that. So yeah, maybe this might like confuse you a little bit. Okay, but look, I'm gonna solve it, just like electric circuit, any electric circuit. It should be very easy, just like the one before. At the end, when I calculate the power generated and the power consumed, I'm gonna teach you, or let you know what is the trick here. Okay, again, if you didn't understand the trick, also it's easy. You can solve it like any electric circuit, very easy, and you can even verify the law of conservation of energy, also very easy. But there is a trick to understand why the power generated is negative, as we're gonna see. Some of it, part of it. Okay, so let's check. So we can do exactly the same. So this circuit can be drawn like that. So this 10 ohm and 10 ohm can be just one ohm, one resistance is 5 ohm, and we can these two resistance can be one resistance. So this again further can be reduced to this in here. So one resistance 10 ohm. So from KVL, let's assume this is a voltage of the resistance. This will be the voltage of the 15. This will be the voltage of the 5. Okay. I'm gonna assume this is a positive direction. So anything matches this direction will be positive. Anything against it will be negative. So this is going up. So like the 15. So the 15 will be positive. Now this is going down while V is going up. So minus V. And this is going down. Also the direction is going up. So minus 5. This is equal to 0. So from here, 15 equal to V plus 5. Or V is equal to 15 minus 5 is equal to 10. Oh, so we know the voltage of the resistance. Once you know the voltage of the resistance, then the current I equal to the voltage divided by the resistance value, which is 10 again. So this will be 1 amperes. So it's exactly like the first one. Okay. For this circuit in particular, you have also this, kind of thinking that you might have, which is also correct. You can say you have here two batteries, 15 pushing up and 5 pushing down. So the resultant, the equivalent will be 10 pushing up. And from that, look, the voltage of the resistance will be 10. So 10 over 10 will be also 1 amperes. So we determine I. So let's go now our original circuit. So we know now this is 1 amperes. And this is I1, this is I2. So by common sense or the current divider rule, current divider rule, just like the previous example, I1 will be equal to I2, will be equal to I over 2, will be equal to half amperes. Now let's apply the conservation, the law of conservation of energy. Okay? So the power number one, the power generated. Okay? So look, guys, we have here the 15, positive, negative, and we have here the 1 ampere. I equal to 1 ampere. Then you have another battery, negative, positive, 5, and the current still going up 1 ampere. Okay, good. So B generated is equal to 15 multiplied by 1. The bigger battery matches our assumption. Our assumption is that the current and the voltage are in the same direction. So that's okay. Now for the second battery, it is like that. The voltage is in that direction. The current is 1 ampere going up. So it can be assumed minus 1 ampere and going down. So it will be plus minus 1 multiplied by 5. Or 5 multiplied by minus 1. It's okay. So look, guys, this is power generated. This is understood. But how come the power generated is negative? How come a battery, a source, generate negative power? Oh, that means this battery is charging. So there is battery here that this charge, it's a charge. It feeds other elements, okay? And now one of these elements that is fed by the 15-volt battery is another battery. So it's like a battery, it's charging another battery. Okay. So you know, guys, these rechargeable batteries at home from Amazon or whatever, Energizer or whatever. So you put them in the charger, okay, and this charger you put in the outlet, okay, and you charge the battery. So you take this battery and you put it in your remote, for example, and use it for some time. So during that time, the battery that you charged was discharging, was feeding until it depleted. Then you bring it back and put it in the charger. So you have like a bigger battery, your outlet now, okay, which is charging another battery. Okay. So that was discharging or basically energy generated. And this is actually energy consumed or power consumed. Okay, let's write per second because it's power per second. It's power. Okay. So this, although it's as a source, but here, you know, by math, it's a negative power, which is of course not correct. But physically, it is, you know, the current is different. The current is opposite. So it basically consumed power. So that's basically 15 minus 5, it is 10. Now let's, you know, number 2, calculate the power consumed. The power consumed, you have econs. You have 3. You have this one, you have this one, you have this one. So the 5 ampere, I'm sorry, the 5 ohm has 1 ampere, so I square R, so 1 square multiplied by 5. This 10 ohm here has I1 is half, so I square R, so half square multiplied by 10, plus again, I2 is half, square it, multiplied by 10. So again, 5 plus 2.5 plus 2.5. Oh my goodness. Again, so 10 watts power generated, 10 watts power consumed. So again, the law of conservation of energy didn't fail us. It verifies our solution. Okay, guys, finally, the last, you know, example in here. So this example is basically with the current source. I'm just showing you, you can apply this to the current source as well. It's very easy. Okay, so I know you are now experts, guys. So guys, very easy. This is 2 amperes. These are two resistances in parallel, has the same value. So by common sense, this current will be divided equally. So 1 ampere will go here, 1 ampere will go. You can verify by KCL, current divider rule, whatever you like. Okay, guys. So we solved everything because now we can apply we can find the power generated and the power consumed. Let's do that. I'm gonna start by the power consumed. Power consumed. So again, we have the power in 5 ohm, we have the power in this 10 ohm, we have the power in this 10 ohm. So the power in the 5 ohm, you have a current 2 amperes, this 2 amperes. Okay, so 2 square multiplied by 5 plus. You have 1 ampere, 1 square multiplied by 10 plus 1 square multiplied by 10. So this is basically 4 multiplied by 5, right? 4 multiplied by 5 is 20. Plus 10 plus 10 equal to 40. Number 2, power. Oh yeah, power generate. Yeah, power for the power generated, we can't, you know, we have to find the voltage first. So for the current source, we're gonna assume the voltage is the same in the same direction as the current. This is volt, but this is easy to find. So let's find it. So I'm gonna apply KVL in that loop here. Anything in our direction will be positive, anything opposite to our direction will be negative. So we have here the voltage of the resistances like that. We have here the voltage of the resistances like that. So this resistance here, it's voltage in the same direction of the positive voltage. So KVL So we have 1, the voltage of the 10 ohm here, this resistance is the current, which is 1 ampere multiplied by the resistance 10. Then for that 5 ohm, its voltage is going from right to left. So it is matching our positive direction of the loop. So its voltage is the current multiplied by the resistance. So 2 amperes multiplied by 5. And now the voltage of the current source, which we don't know. We know the current of the current source, but we don't know the voltage. It is going up opposite to this way. So the direction is going down, it is going up, so it's negative. Negative V equal to 0. So V is equal to 10 plus 10 equal to 20. 10 plus 2 multiplied by 5, which is 10. So 10 plus 10 is equal to 20, 20 volt. So the voltage across the current source is 20 volts. So we have a current source like that. It has a voltage in this direction equal to 20 volt. And it has a current in the same direction, 2 amperes. So number 2, the power generated equal to the current multiplied by the voltage. Oh my goodness, again. 40, right? So 40 watt here. And 40 watt here. So again, the power generated equal to the power consumed. Thank you very much for watching and see you in another video. Bye-bye.